Hi, my name is Fox. Welcome to Automation Workshop. We are in the section of PLC and relays, where I'm going to take you through the introduction of PLC. A PLC is an industrial computer specialized for real-time applications. PLCs are integrated system containing a processor, main memory, input modules, output modules that are coupled together by a common bus. Input modules interface with the plant equipment and converts the field signals to logic level for the processor to read. The processor uses these inputs to perform control functions based on application software. Output modules transmit signal via an interface with the plant equipment. As you can see on my picture below, I have the architecture of a PLC that shows how a PLC is built. It consists of CPU, user memory, data memory, and serial port. On the serial port, it's where you connect or you communicate with a programming device, of which will be your computer. Well, there are different forms of communication. Some PLC, they use USB, some they use Ethernet, some they use Profibus, Profinet. As we continue with the lesson, we're gonna touch on those. It has input modules, it has output modules. On my demonstration sensor, they are connected to the input module. Then the input module sends signal to the CPU. The CPU executes the decision that the user program for that particular PLC to do that particular job. Then based on the program on the PLC and the state of your process, based on the information that your input will bring onto your CPU and the algorithm that you have written, then your CPU will update the output which is connected to your actuator. Then your field device will do what you program. Well, there are many types of PLC and they vary significantly in appearance, in capabilities, and in size. But almost all of them, they somehow have a common function. So before PLC, this is how the control panel used to look like. In this control panel, we can see we have a time relay, we have relays, we have contactors. Prior to PLC, control tasks were often performed by contactors, control relays, and other electromechanical devices with intricate interconnection wires. The approach is often referred as hardwired control. If you go to electrical workshop, you learn about the hardwired control. Although hardwired control solutions are capable of performing some of the same task as PLC, hardwired control is generally more difficult to design, install, and maintain. In addition, the process of making even simple modification to a hardwired control solution can be difficult because the logic of the control system determined by interconnection of wires and components. And another problem is that now let's say your system have a problem, you want to troubleshoot. It's hard to do troubleshoot on a hardwired control. Sometimes you'll have to work with more than 3 relays for you to have a control system. And let's say one relay is no longer working, and for you to know that the one relay is no longer working, hence your system is behaving this way, it's going to be hard for you to do troubleshooting, though you will be able to do troubleshooting because of the skills that you gonna learn in electrical workshop, but it will take you time. Hence, we have PLCs. PLCs can perform more complex tasks. PLC can communicate with other systems. PLCs systems are more reliable. PLC systems are easy to operate and maintain. PLC system can you can do changes easily. You can implement changes easily, and PLC application can be duplicated faster and less expensively. Well, all PLCs they have this basic operation. We call it PLC scan cycle or cycle, where a PLC will read the input based on the program written on the PLC. It then executes that program, updates the output, communication, then diagnosis, then the cycles repeat. On my right hand side, I have the architecture. The basic components of a PLC include input signal module, a central processing unit, of which is CPU, output signal module, and programming device. The types of output and input signal module used by a PLC depends upon the type of input or output device used. Let me talk about input signal module. Input signal module converts the signals provided by an input device into logic signal that can be used by CPU. The CPU then uses the values of the input and output and other variables as it executes the user program stored in its memory. The CPU then the CPU will send the signal to update the status of your output. Then let me speak of output signal module. Then, based on the signal the output module received from a CPU, it will then convert that signal from CPU into digital or analog that can be used to control your output devices. The programming device that is used, it can change, it can modify, it can monitor what is happening. With a programming device, you can actually see what is happening in the field based on the inputs that are connected to the CPU. Then you connect your computer to see, okay, push button is now pressed, the limit switch is now closed. So we also have another thing, we call it a control system. Your control system may be incorporated by one or more human-machine interface. Human-machine interface is abbreviated as HMI. We use it to monitor and control a machine or process. HMI are not PLC component, but they work closely with a PLC. When it comes to the selection of a PLC, it depends on the project or the job that PLC is expected to do. When selecting a PLC, you must check your digital I/O, of which is the number of your digital input output, the number of analog input or output, the number of communication ports, if that particular PLC is capable of expanding your IO module, and you should check also the processing speed of that PLC, how fast that the cycle can repeat itself, like for how long can that PLC read the input, execute a program, update the output, how fast can that PLC be. All those things, you select a PLC based on your application or your specific job. Each PLC comes with its own programming software and the number of programming language, which will depend on the manufacturer. Keep in mind that all PLC operation are the same. The more you spend time with them, the more you will become a good PLC programmer. Like you master that particular PLC, the more you spend time with that particular piece. And to diversify, to learn other PLC also gives you that advantage of being able to troubleshoot or to program any PLC. If I give you any PLC, like it's a PLC, I can program it. Just give me a programming software and give me a technical datasheet where you will see all the where you can see the properties of that particular PLC, to check how many input does it have, how can you do wiring, but we're gonna get there. The capability of a PLC can vary from simple switching on and off. If you press push button, then your light will come on or off, to monitor, to monitoring. So we can simply use PLC to trigger light, switch it on and off. We can also use it to monitor and controlling a soft drink manufacturing plant. It means that the capability of a PLC depends on one's ability to develop a working program to reach the expected desire. So it requires one to think outside the box to be a great PLC programmer. You will have to think outside the box if you are a PLC programmer. In the workshop, these are the PLCs that we have. We have Unitronics, which is a PLC plus HMI. It's a PLC that has human-machine interface. As you can see, it has a touch screen. On my top left, I have Allen Bradley Micro 820. When we are doing PLC, advanced PLC, this is the PLC you're going to be programming. On my below left, I have my logo, Siemens logo. It has 4 relay output. I have a Schneider. We have ABB. So all of these PLC, they are able to read, execute, write in the update your output. The only difference in them is that some they have more input than other. Some they have analog input. For instance, let me start with a Siemens logo. Here I have 8 digital inputs I have 4 digital outputs which are relays. I'm going to explain the difference between a relay output and a transistor output. Let's say we check micro 820. Micro 820, it has more outputs than logo. Let's jump to ABB. This ABB, it has about 6 digital inputs, 2 analog inputs, then it has 2 analog outputs. So in selecting a PLC that you're gonna use for your project, it depends on these factors: the number of your input outputs, the processing speed, the communication port. As you can see on the ABB, we have 2 communication ports. We have Ethernet, we have RS323, we have Ethernet on Schneider. It depends on a PLC. So one may ask, we have a lot of PLCs. Why, if I go to Sasol, I find them using RS Logic 5000, of which is Allen Bradley. If I go to Unilever, I find them using ABB. If I go to other factories, I see them, they are using Siemens. It is based on what I was explaining, that the capability of a PLC, that there are things that you have to look at when you are selecting a PLC. Things like your digital input, your digital output. Let me speak about I/O module. The input peripherals are the module used to input information into PLC. Information such as state of the sensors, and it uses the output module to communicate with output field devices. Well, we have 2 types of signals. We have analog signal and we have digital signal. As you can see, analog signal is continuous. It varies. Some, they vary between 0 to 10 volts, some 4 to 20 milliamps, some it's 0 to 20 milliamps. Signal which only have 2 states. It's either high or low. It's either 0 volts or 24 volts. So here I have push buttons. Push buttons can only give you a 0 or a 24 volt if you are using a PLC that is supplied by 24 volts, of which will be your 0 or your 1 in binary. Then this side I have a differential pressure transmitter, which will give you a 4 to 20 milliamps. 4 to 20 milliamps. So let me erase. Now we know the different types of signals. When we go to instrumentation section, you gonna understand much better about these signals, because when we go to instrumentation, then you'll find different types of instruments based on different types of application. Earlier on, I said I'm gonna explain about the difference about the outputs. We have two types of, well, there are three, but my main focus will be on these two. We have relay output and we have transistor output. So before you can wire any PLC, you must understand, or you must know, if that particular PLC has relay outputs or transistor outputs, because your wiring will be based on that knowledge. Because other PLCs, they have both relay and transistor output. You see, the PLC that you're gonna be programming for your basic PLC programming, it's gonna be logo, Siemens logo. This is the PLC. It has about 4 relay outputs. What you apply on Q1 is what you're gonna get on M1. Let's say Q1, I wanna control an LED that only requires 5 volts. For me to switch on and off that LED, I'll put a 5 volt power supply, on my Q. Then on my M, I'm gonna connect my LED, then complete a circuit. Let's say on my Q2, I wanna control a relay, a 24 volt relay. Then I'm gonna put my 24 volts on my Q. Then I'm gonna put the coil of the relay on my M. As you can see on my diagram. With transistor output, I have grounded my output module, and I have applied 24 volts, so I've powered this entire module. Ne? So any output that's gonna be connected to this I/O module will have a common power supply, of which will be this one, where you're gonna connect it at 2M. It will control these output, of which will be 1, 2, 3, 4, and these 4, 1, 2, 3, 4, also they're gonna have their own power supply if you don't wanna use the same power supply. So with transistor, your output module must be powered. But some PLC, they have both transistor and relay, just like the PLC that I have here. It consists of 4 relay output, 1, 2, 3, 4, and 2 transistor output. Ne? With transistor output on M, I'm powering the module. With relay, I connect power with like I power individual output. Q1 is individually powered, Q2 is individual powered, Q3 is individual powered, Q4 is individual powered. Well, the way it's connected here, it's because I have the same power supply for 4 of them, and I can either connect an AC voltage of that will range between 0 to 250 volts, or I can connect a DC that will range between 0 to 30 volts. Now we know the types of relay PLC outputs. Let's move to the programming part. Okay. We have different types of PLC programming language, such as structural text, function blocks, sequential function chart, instruction list, ladder, diagram, and many more. But in this session, we will focus on one that is mostly used of, which is ladder. Ladder programming is intended to be used by anyone without any great knowledge of programming. You don't need the rocket science of programming, like you are programming like C++ or Java or Python. It can be adopted by most. I'm sorry. It was adopted by most PLC manufacturers. However, each intended to have developed their own version. Though you may find Siemens logo ladder and Allen Braid ladder, there are things that might not be the same, but the structuring of both will be the same. It was originally a written method documented the design and construction of relay rack as used in manufacturing and process control. Each device in rack will be represented by a symbol on a ladder diagram with connection between those devices. Each rack must start with input or input and must end with at least one output. So it was actually the migration. The ladder was the migration of a relay circuit design, as you can see on my picture. This is how you will write your relay circuit. Then, as the real pass picture shows us, that it then move to be like this in a ladder. The ladder, this is the code that you're gonna write on your PLC, where your start button, your stop, is now here. It's a normally closed. Then you have a start button that is latched by KM, same as this one. Start is latched here. Then I will have your overload, and this is your overload. Then you have your coil, and this is your coil. So in relays, this is how you represent a coil. In PLC, this is how we represent coils. Then these are the contacts that we're gonna be using. This is a simple example of here on top, a simple example of a ladder instruction. When you press start and you also press your start 2. Let's say your start 2, it's your stop, and your stop button is normally closed, then your motor will run. The moment you stop, you release your start, your motor will stop. So building a PLC ladder, you'll have a line on your left which will represent your power or your positive section. Then on your left you'll have your negative. So power will flow, or current will flow from positive to your negative. So you will have, let's say you wanna control a light, like the example on top, or this is for the motor. You will connect your input, then the coil of your light. Okay, then this will be your output, will represent output as Y. Let me say Y0000, and call this one X001. So on your output module, let me go back to show you. You see, I have Q1, I have Q2, I have Q3, I have Q4. Ne? When you are programming, you will have to give Q1, Q2, Q3, Q4 address. Also with your input, you will have to give them addresses based on that particular software that you are using. Addressing differs with the software that you will be using. Okay, so that my start, the address will be X001. My output will be Y000. When I come to wire it, this will be my output, this will be my 000. Then that's where I'm going to connect my motor. Then on your input also, you will connect according to your address, the way you've addressed your input. So when you are programming a PLC, you must address your input and your output. Well, with the PLC that we're going to be programming in the workshop, what's nice is that on the software, your input, they are already addressed as I1, I2, I3, I4, I5, I6, and your output are already addressed as your Q1, Q2, Q3, Q4. But other PLCs, you will have to address them. Like when we move to Allen Bradley, you'll have to give each address, each input or output address. So here I have the basic program using ladder. The following circuit is used to start and stop motor using a push button. In a normal state, a push button A is open and a push button B is closed. When A is pressed, the motor will start. When A is released and a holding contact maintain the circuit, hence the power, hence the power to the motor. This will be your latch. I'm going to explain latch now. Then you'll have B to stop. Whenever B is pressed, it will disconnect power. Remember I said on your left, it's where you'll have your positive. So it will cut power from powering your coil. Then this won't be powered. When this is not powered, this will go back to its initial state, of which is being normally open. Okay. So in the workshop, Siemens logo, the PLC that you're gonna start with, this is the interface. This is how the interface looks like. Number one, I've explained that will be your power. Then number two, it's your contact for your start. Number three is the contact of your stop. Number four is what we call a memory bit or a memory flag. So it's a coil that is internal. It's an internal bit. You won't have any physical port where you will connect your M1. It is an internal flag. Ne? So we need flags to achieve some of the programs that we want to achieve. For instance, here, when I press the start button and your stop is closed, power will go to your M1 and M1 will be energized. Then it will latch, then your M1 is energized. Whenever M1 is energized, this one will also change its state. When this one changes the state, then your Q1 will light up. Okay? I can use this M1 for other things in the program. On number 5, that's where you'll find your contacts on the software. Number 6, that's where you'll find your special functions like your timer, your relays, your time delay, your counters. Then on number 7, it's where you're going to see the real-time simulation, what is happening. If you press a button, then you'll see on number 7 the state change. So one may ask, why now my stop it's a normally open? How will then my M1 be energized if my stop is a normally open? Okay, so it is better. That's actually the better way of wiring and programming your stop. It is an actually safe way. Ne? A better arrangement is to program the stop switch or the button in a ladder program as an open and use a stop button or switch that is a normally closed. Ne? And operating opens it. Ne? So your physical push button for a stop will be a normally closed. Ne? Then on a PLC you declare it as a normally open, as you can see here. Yeah? Why do we do this? Like this is the way. Because if anything happen along, let's say here you have your 24 volts. Let me draw it nice. You have your 24 volts positive. Then I have my stop. Then I have my let's say it goes to a function block. Let's say it goes to a PLC. I'm sorry. Let's say now something happens and this wire is cut here. The PLC is no longer receiving at 24 volts. Your motor will never run, because for your motor to run, this normally closed will change the status of this normally open on the program. Then this normally open will be a normally closed as long as this is closed. So whenever there is an emergency on your system, when you press your stop button, it will break and the PLC won't be receiving any voltage. Then the state of your PLC will change from a high to a low. Then there won't be any current flowing here. Then your motor will then stop. But if you have connected your stop button as a normally closed on your program, that means your physical stop button must be a normally open. This is dangerous, because now let's say here by mistake the wire is cut and the machine is running and it's about to cause problem, so you want to stop it immediately. When you come, you press your push button, your stop push button, the PLC won't receive any signal and that emergency won't stop. So it is always safe to connect your stop button as a normally open on a PLC, and physically you get a normally closed stop button. Okay, let's move to function block. Function block in a PLC are used to perform additional operations such as delay, mathematical operation, maintaining information, converting and comparing, and many other things that you can think of. So here I have a time on delay and a time off delay. For your output to be a high with a time delay, your input or your timer must be a high. Yeah? Then for this period, when it's high, this will be your delay. This is your delay. Let's say this will be your 10 seconds. The moment your input is no longer receiving power, your output will be off immediately. Unlike the off delay. Ne? For an off delay to start counting, your input must be high. Ne? And as long as your input is high, your output will be high. The moment you cut your input, then your delay will start counting. This is the duration that it will count. Look at your output. Your output, it's still high, it's still on. It will be off when the time that you have set has elapsed. So the difference between the two is that a time on, of which is TON in most PLC, your input must be high. It will delay before your output comes on. But with a timer off, most PLC, you'll see it as TOF. Your input must be high. As long as your input is high, your output will be high also. The moment your input is low, then your delay will start counting. The moment it reaches the time that you set, then your output will be off. Okay. Let's move to let me erase. So this is before we move to counters. I want to show you a simpler graph. This will be your input for the time on delay. Now your input is high. You see your input is high, but your output is still off. And this is where your timer will be counting. The moment it reaches your set point, then your output now is a high. The moment you cut your input, your output is off. Then here, your input is high. Remember, for your output to be high, there must be a delay. Then it start counting. But before it reaches the set point timer that you have set, then it goes off. Nothing will happen on your output. And here, let's say you trigger it again, then your output then comes in. Then you immediately cut your input. Your output will also reset. With the output, remember I said you must have your input must be first on, then your output will be on also. This will be your output on Q. But you see on what I'm drawing, your output will remain on even if your input is now off. Remember your okay, my graph is not accurate. Okay, so my input is high, my output is high. My input is now low, then my output start counting. The counters count. When it reaches the set point, then my output is now off. When you trigger it, it will be high. Ne? When it goes off, your output will remain high. It will remain high. until it reach your set point time. But let's say before it goes off, then you trigger your input again, your output will remain high. It will remain high until your input is off. Then your counter for the time off will start counting. When it starts to continue counting, then you again trigger your input. It will then reset the counter that it was counting, then be on. When your input is off, then start counting for it to be off. I hope it is loud and it is clear the difference between your input and your output with your time delays. That a timer on, for your output to be on, there is a delay before your output be on. With the timer off, it is on immediately and turns off after your input is off. Then we have latch. We have SR latch and we have RS latch. Before that, let me explain what is a latch. So a latch is used to maintain the output as high as soon as the input has been triggered, and the output will go low as soon as you reset or you press stop. Let me take you back. Here I have the latch, the basic of latch. When I press A, power will go, energize, output O. When the output O is energized, this will change the state and it will allow power to pass through. Even if I release A, power will be flowing through, passing through this contact, powering your output. So this can be achieved also by the function blocks. The function blocks, we call them RS and SR. SR prioritize set over reset, and RS prioritize reset over set. What do I mean? When set input is a monetarily true, like when you press your set and it remains true, and when you press your reset, let me highlight it. I press my input, my latch set, and while it's still pressed, I press reset. Both of them same time they are pressed. This flip-flop or this function block will prioritize set and your output will be set. Ne? But with the RS, it will prioritize the reset. Let's say your input is pressed and you hold it. While it's held, you then press your reset. This will reset will reset your output. Ne? But when both of them, the working principle is the same. The only difference is when you press both set and reset same time. But in a normal condition, when I come, press the input, then I release, and I come again, I press reset, it will reset. Ne? Also this one, when I press the set and release, it will set, it will latch, your output will be latched. When I come, press reset, it will delatch. But if I press both set and reset on SR, your output won't reset. If I press both set and reset on RS, your output will reset immediately. Then we move to my last function block of the day will be counters. Counters are used to count the amount of object for certain application. The PLC provides up counter, of which on a PLC will be written as CTU, a down counter, CTD, a combination of both up and down counter. So, how does a counter work? A counter, you set your preset, your set point value. Here I have 3. Yeah? Then whenever I press this will be 1. I release, I press again, it will increment 2. I release, I press again 3. The moment it reaches 3, my output will be a high. Then I come, I press a reset, then it will reset everything. Yeah? With a down counter, let's say my preset value is 3 again. When I press here, here I'll have 2. I release, I press again, I'll have 1. Ne? I press and I release, you press for the third time, then you have a 0. Then your output will be a high. Okay? Based on the function that you're gonna put on your set to say, I want my output, like you'll declare, let me write it, you'll declare to say, whenever my PV is, not your PV, sorry, your Q, of which is your output, whenever my Q is equal to 3, then I must have a high on the output. Or whenever my Q is less than 3, then I must have something must happen. Then we have the last one, of which is up down counter. This one you can both increment and decrement. When I press the up counter, it will increment. When I press on this sensor A, it will then decrement. But the moment I press reset, it will reset everything into 0. But with the PLC that we are programming in the workshop, this is how an up-down counter looks like. In input pulse, increments or decrement and internal value depend on the parameters setting. Okay, so with this one, the PLC that you're gonna be programming, as you can see, it has one counter. Let's say this is how you're gonna wire it. This will be my counter, then this will go to your function block. Ne? Okay, so it has reset, where whenever reset is pressed it will reset the number. It has a direction, ne? So the output set or reset when the configured threshold is reached, ne? The direction of the counter can be changed with the signal at the input. So for this to count up, there must be power that you are powering your direction. But now let's say you are no longer powering your direction. What will happen? Whenever I press here, it will decrement. But if this is closed, it will increment whenever I press a counter. That's the nice part of this local PLC. But other PLCs, as you saw here, that it has a port for counter up and a port for counter down. But with logo, it has one port for counters, for up or down. You just have to change the direction. That brings us to the end of this session. Be safe, guys. If there be any question, please drop it below, or let us discuss it on the group. Have a great day. Thank you. See you in the workshop.